some level of running notes because it'll just be more tractable. Yeah. The main issue is that, we are traveling through many universes as we are making our way through this course on non-equilibrium and nonlinear. That's what we're trying to cover. And thus far, I have focused more on non-equilibrium and very little on nonlinear, except when I touched on the Fermi-Pasta-Ulam single problem. So that is kind of the holy grail of a problem. But there are more, and I need to change gears. And you also need to mentally change gears because we are entering from a universe in which things are more or less understandable and solvable, or at least, well studied, to a universe that is relatively poorly studied, primarily because of the difficulty involved. And the difficulty involved is paramount in this case, because anything nonlinear tends to become somewhat impenetrable very quickly. And we also lack insights. I think that's a very important thing to keep in mind. When we do nonlinear physics, or nonlinear dynamics, or nonlinear dynamical equations, whatever you call it, the subject was started by a combination of mathematicians and physicists, but the subject now resides more in the domain of mathematicians right now in 2026 than in the domain of physicists. Physicists have gotten a bit distracted with the developments in quantum, but more is in the applied math domain. And I kind of live in both of these worlds, though I am a physicist. So historically, it was like that. It was kind of 50-50. Now I would say it's more like 80-20 or 85-15, where 15 is the physics people and 85 are the math people. By the way, most of these math people are PhDs in physics, excepting they have math physics type PhDs or they have moved into math departments. Very common. Anyway, so we have done this diffusion equation problem, which is a relatively straightforward problem. One thing I wanted to mention, and I think this is important for you guys, not for you guys to know, that is, there is a very, very nice book on mathematical physics that is not very popular yet. Maybe it is. As far as I know, it's not. Historically, people have used to teach mathematical physics using a relatively simple book called Arfken's Mathematical Methods for Physicists. Arfken is Arfken, George Arfken. It's a very classic book, just like Jackson's Electrodynamics. And then there are older books. For example, there is a very, very good book by Butkov, Butkov, Butkov. And then, of course, there are difficult mathematical physics books, which are very abstract, like that by the 2-volume set by Courant and Hilbert. That's very old now. These are classic books. And in recent times, it's Arfken or Boas, which is a slightly lower version than Arfken. These have most commonly been used. Tony, you may have used one of these.
Used Mary Boas.
Yeah, that's another very common one. It's a little bit lower. Arfken is more like a first-year grad, and Boas is more like a junior senior level. It's kind of in the transition. Yeah. Now, there is a very nice book written in around 2010 or so by a very distinguished physicist, in fact, a National Academy member. His name is Gerald T. Mahan. He has passed away now. And it's not called mathematical physics. I have the book in the other room. It's I think it's something along the lines of applied mathematics for physicists or something. I'm going to put a question mark because I'm not 100% sure about it. Jerry Mahan was a no-nonsense, serious, world-renowned theorist. He was actually a man with great humility and with a very refreshing sense of uh, British-style humor, where he would throw something out and it was very funny, but he would be uh, as serious and straight-faced as you can imagine. So I got to know Jerry Mahan much later in life, for him and for me also. I was young, he was quite old. I'd invited him to Buffalo. Uh, there's a book called The Many Body Problem. I mentioned that in this to you guys long time back, and it is written by the same fellow, G.D. Mahan, Gerald Mahan. And this book is about 1,200 pages in size. Okay, it's also in the other room. So Jerry Mahan, when he published this book, in the preface to the book, he questioned his own sanity to have written something that big. And true to his words, uh, beautifully written, very clear. Every sentence is self-explanatory. But that's what happens when you write it that way. The book becomes super long, and we covered the entire many-body problem, which is like 50 problems probably. It's fantastic. But this particular book, true to Jerry Mahan's nature, is a very comprehensive, very detailed, and very to the point, matter of fact book. It's more advanced than most books I've seen. Uh, Certainly more advanced than Orfkin and probably Budkov also, but more updated. And the reason why I'm bringing it up in this particular slide is because Jerry Mahan discusses about 4 or 5 examples of real life use of the diffusion equation. And I was so tempted to cover all of them today, but I took a decision against it because my argument was, after all, I'm not trying to make my students into diffusion equation uh, experts right now. My goal is to introduce it to them such that they know how to basically use it. But Jerry Mahan does a slam bang job of expanding on what I did. Very rigorous, very clear. Strongly recommend that even if all your mathematical physics books burn down, this book is worth holding on to because it is that good. Okay, so I didn't want to forget about that. So anyway, so we did all of these, the kind of Fourier transform, Laplace transform game, and it gives practical tips. He said in most of these problems, you probably can do with just one transform instead of two, and stuff like that. So very serious, very good person. Anyway, so now we are entering this rather bizarre universe of nonlinear effects, nonlinear waves. Is it basic? Is it like fundamental science? Is it applied science? And the answer is it's both. Is it a frontier area? Yes, it is a total frontier area. Although the area has been around, as I said, for a long time. And one of the key problems that we face as a community is how to understand these two words, integrability and non-integrability. And this, as I said, I gave you the example. This is about as basic as you can get in the spirit of Flexner. That why does it matter? Well, it shouldn't matter, but it's really important to know because without it, you may have trouble. What kind of trouble? This kind of trouble. You may drown. That's serious trouble. Is that basic or is that applied or is that both? Or this kind of trouble, as I was showing you guys on Tuesday. Is it basic? Is it applied? We don't know how to manage rogue waves. In fact, Ships still issue maydays because of rogue waves. I lost one of my cousins, 3 years older than me. He was a ship captain. He went down in the Bay of Bengal in 1995. He was 38 years old. And I don't know if it was a rogue wave, but it was a very, very stormy sea just outside Rangoon, which is the new name of it is something else. But anyway, um, in Burma, in Myanmar. So rogue waves are very, very dangerous, very, very real in the lives of people. These are all problems that come because we can't solve these problems. And we can't solve these problems in particular because we are grappling with the basics of what can be integrated, meaning what equation of motion can be integrated versus what equation of motion uh, cannot be integrated. Now, that said, there is more nuance to it. For example, there are equations of motion that can be integrated in, let's say, nice closed form and very manageable, no problem at all. You can pretty much do anything you want to do. It may be mathematically difficult, but it's doable. But there are equations of motion that are actually quote unquote non-integrable. They can also be integrated, but you cannot find good closed form solutions. And that inability to not make a perfect closed form solution turns out to be the killer. So you may have a 0.005% error because your solution is not closed form and not exact. And that 0.005% error is good enough to change the outcome at some point late in time. That's that's how I understand non-integrability because I have experienced this. I've constructed a solution. The solution is incredibly good. Uh, People cite it all over the world. 2001, 25 years old. But the problem is non-integrable because the 0.115% or 0.05% error that this solution is unable to catch is good enough to drive the system to unpredictability down the road. It may get you to the ballpark, but it doesn't get you to the real solution. And sometimes getting to the ballpark is not enough. That's why. So just to give you a perspective, so you can do your own journey on nonlinear equations without having to do too much work because I have done the work for you. Let me pull up the slide with which we finished, which is this slide. And I said that back in the 16th century or so, there were all these physicists and mathematicians. At the time, there wasn't much difference between the two, who got involved in understanding waves because waves were an existential challenge to the existence of the healthy economies of the colonial European monarchs. By the way, ironically, American economy today still runs in the colonial mode because we basically pump money into the Army, Navy, and the Air Force, and they are the ones that fund everything, including most of basic science and applied science. So we still live in that colonial mindset, which of course I'm sure will change, but this is how it is even now. Most countries have a healthy defense budget, but America's defense budget is pretty much, you know, a major piece of the economy. So all these people played, incredible roles in this development. And the key name to keep in mind here is the name who is last from the bottom on the right side. And that is Korteweg
Korteweg.
and De Vries. Korteweg and De Vries in 1895 finally got something. Now I say finally got something because the journey didn't begin and end with Korteweg and De Vries. The journey began with Benedetti back in the 1580s, 300 years ago. And over those 300 years, our understanding of waves developed in some way, shape, or form. And there were a whole bunch of equations that emerged along the way to describe, wave phenomena under various contexts. Many of these equations uh, are perfectly normal, perfectly healthy, perfectly correct. They're even around today, accepting that they have turned out to be perhaps not the best way to get to a problem. So the finessing of the problem took place over these approximately 300 years. There are equations written by Businesq, which is pretty nice actually, and connects with all of these guys. So Businesq equation is very much around still. In fact, if we have time, I hope to spend a bit of time on the Businesq equation problem. So Korteweg and De Vries, what did they do? So I'll tell you a little bit more about them. I wanted to show a solution, the way of constructing a solution to the Korteweg-De Vries problem. But thus far, I haven't figured out uh, if I want to do it, or if so, how I want to do it. And that also is a very interesting point to keep in mind so that you follow. You see, Korteweg and De Vries problem was very difficult to solve, obviously. However, later on, as we developed our mathematical machinery a little bit, it was realized that the Korteweg-De Vries form and many of these forms can be tackled by something called the inverse scattering method. I mentioned this to you guys earlier. Inverse scattering method is a nonlinear form of Fourier transform. It's a Fourier transform type thing which is meant for nonlinear equations. And this inverse scattering machinery is what is typically used for solving Korteweg-De Vries nowadays. So for me, the question is whether I want to develop inverse scattering for you guys. And my gut tells me it's not worth it because this is almost like, a chunk of the cost then should go to inverse scattering. Inverse scattering is a very versatile method to use. And I can't do justice to inverse scattering, which I myself am not an expert on, in a relatively short 1 or 2 week time frame. It won't be good. So I may actually skip doing Korteweg-De Vries unless I can find some other way of getting around it, which I'm sure exists, but I haven't taken a decision on whether I want to show you this or not. But let me also tell you that Korteweg-De Vries is not the end of it after all. So this slide is very important. So this slide summarizes pretty much everything we want to know about integrable systems. On the very top is the very well-known and very friendly wave equation. And the little thing that is here is showing you what a wave equation is describing. Basically a moving wave, a plane wave in this case. Now, so that's the wave equation. That's your linear equation. X minus vt comes in. And the wave equation essentially is a wave moving at fixed speed. And the amplitude is also something which is very simply behaved. Now, there are three major solvable nonlinear wave equations. Okay, three. These have been studied to death, continues to be studied to death. Techniques are being refined and grinded out by trying to solve these equations in more manageable form, or their variants in more manageable form, which brings us to the issue of variance. These three equations ultimately dictate a family of maybe 15 or so equations, maybe a little more, which are solvable nonlinear equations. But the mothers are these three guys. Sine Gordon is a wave equation, but with the sinusoidal term, right? Because UTT is d2u dt2. This is d2u dx2. So that's a wave equation in 1D. But then there's this b sine of lambda u term. Sine term is obviously nonlinear. It's a power series. I already told you about the Korteweg de Vries. Korteweg de Vries is here. Du dt plus u times du dx plus b times d3u dx3 equal to 0. So the Sine-Gordon equation describes this problem. I don't know why this thing is not playing, because this should be playing. Whoops, it's not playing. Let me take it off. Let me show you here. That is your Sine-Gordon equation. See, here the pulse propagation is so unique. It's like something is going around like this. But it's a pulse movement. See, the pulse has no tail. Observe it very carefully. It's just a pulse. It restores it back to original form once the pulse passes through. That's a typical example of what we call a soliton. This is another soliton. This is the Korteweg de Vries soliton. An actual photo. And in this soliton, in this problem, what you have is a shallow canal. And it's a long canal, meaning that the width of the canal is much, much smaller than the length of the canal. So these are the two conditions. One is the shallowness of it. So the surface is important. And the second is the fact that the length is much, much larger than the width. That's a canal. And then there is something called the cubic Schrödinger equation, or also called the nonlinear Schrödinger equation. NLSE is the acronym by which it goes. And the nonlinear Schrödinger equation is I times du dt, dtu dx2, then a mod square of this u, and then a u itself. Very, very ubiquitous forms of equations that keep showing up in many nonlinear problems. And so what applied mathematicians and physicists have done is they take many of the nonlinear problems and see, just like some dough, if they can mold the problem somehow into either of these three or its variants, which are solvable. That way they can approximate what may be an unsolvable, impenetrable, difficult problem with something that is more solvable, more manageable, and then build from there. So it's like a perturbation idea at the end of the day. By the way, the picture on the top right is real. It is taken from the satellite. Should be survey. I don't know what I've done. And soliton in the ocean, D and S are moors. I don't know what moors is. Solid line is a ship survey track. So this is a ship survey track here. This solid black line. I don't know if you can see it. Or D and S are moors, meaning D and S are where they probably have buoys. Buoys meaning the ones that float in the ocean. So D and S are buoys, and you have this ship survey tracks here. Some work was going on, and this is in the ocean, and this is a photograph that is taken from a satellite in space. And what you see here very clearly are two solitons. Actually, they are solitary waves, I would argue, and I'll tell you the difference later. One is this fellow that's running quite a large distance. You see that? It's from 56 point 475, probably north latitude, up to 56.55 north latitude, a little beyond that. That is a very significant length, certainly of the order of, I would say, 10 to 30 miles, probably. Huge wave. Must be in the open ocean. And here is a weaker one that you see. Not uncommon to see a weaker one after a major one. So these are solitons or soliton-like. I call them solitary waves. I'll tell you why I call them. There are very sound theoretical reasons for it. All right. So you can see that there are fundamental reasons and there are strongly applied reasons. We all want to be able to negotiate oceans. So these, as I said, are the three solvable equations. But notice here, these three solvable equations are continuum equations, right? They're continuum equations. Continuum equation means space point here and space point here are related with an equation here. Simple relation. If you know this point, know that point. Sound propagates in this case through a continuum medium. It's not a discrete medium. We are not talking description at the level of particles and particle-particle interactions. We're talking about a continuum through which it is propagating. Trouble is that there are very, very few systems that are discrete, particles and interactions, let's say springs, that are solvable. Almost none. But there is one. I'll show you that one. And that is this equation by Toda, Murikazu Toda. Vibration of a chain with nonlinear interaction, published in February of 1967. I'm sure people are planning celebrations of 50 years of this paper next year all over the world. 60 years, actually. I'm sorry. Applied mathematicians in particular, I'm sure, but is that important of a paper? It has been a transformative paper. Here you have particles, one-dimensional chain, masses connected by springs, but the springs are not normal Hookean springs. Springs have this interaction. They have an exponential interaction, meaning that the interparticle distance, which is r, if r becomes large, this thing falls off. This thing grows linearly, it doesn't matter, it's a very weak term. And if r becomes small, this rises. So it's an equation with exponential interaction. And Toda managed to solve this problem exactly. We'll study that. But there's something important to keep in mind that I'll bring up again very soon, but keep in mind now that when you write e to the minus br, what are you writing? You're writing 1 minus br. If b is equal to a, and if this is a, then of course the linear term goes away, right? Because it's a minus ar and this is a plus ar. That's one observation. Second observation is the third term will be 1/2 b square r square. That will give you a harmonic term. And then you have a cubic term. And then you have a quartic term. And then you have a fifth order term, and so on and so forth. So this is an infinite series. The linear term is unimportant, because if you take a d phi dr, the linear term doesn't matter anyway. But I mean, it just generates a constant, I guess. But this is actually a series which comprises of r square, r cube, r4, r5 with alternating signs. So this is the main reason, I think, why Toda's solution is a game changer. Game changer. and game changer because it is exactly solvable. Because if you know Toda's solution, then at least you have some hang of how to perhaps understand a little bit of the Fermi-Pasta-Ulamsingo problem. I'm going to pull up the Fermi-Pasta-Ulamsingo problem, which I introduced to you earlier. But let me just remind you, this was the Fermi-Pasta-Ulamsingo problem, where you see the first term is a linear term in force, second term is a quadratic term in force. That comes from a cubic potential. Toda has a cubic potential term, but Toda also has a quartic potential term. That quartic potential term becomes the second term on the right side, this cubic term in the force equation of the Fermi-Pasta-Ulamsingo problem. This guy is called the alpha problem because the coefficient is usually written as alpha. This guy solved the beta problem because the coefficient is usually written as beta. So the beta problem has stronger nonlinearity than the alpha problem. The alpha problem, if a cubic term in a potential becomes strong, potential will become unstable, isn't it? You need even powers in the potential for these guys, mass spring systems, to be stable. You have to have a parabola of some kind or something like that. You can't have it like this going down. So clearly, therefore, alpha is a small quantity. Now, beta, on the other hand, is already an even power. So there is no such constraint required for physical purposes. So what I'm saying is that the Fermi-Pasta-Ulamsingo problem that you have looked at before and will again return to is nothing but somehow also tied to the Toda problem, which gave people a lot of hope. But that hope hasn't panned out quite as one would have liked. By the way, do you know who these guys are? Okay.
And for me,
This is Fermi. This is John Pastor. This is Stanislav Ulam. Stanislav Ulam was a very famous mathematician, by the way. And he had a pretty long life. He was in Los Alamos as well. And the coding and all these calculations were framed on the Maniac 1 machine in 1954 by Mary Single. This is Mary Single. Her name was not written in the publications excepting separately. And in more recent times, people have become very conscious of it. So we call it Fermi-Pasta-Ulamsingo problem as a result. This appeared in a paper by a French physicist, Thierry Deschaux, in 2005, where he introduced the term FPUT problem. But I actually, as far as I know, was also one of those people who introduced the term Fermi-Pasta-Ulamsingo problem back in early 2000s before the Deschaux. So now it is catching on a little more. More people call it FPUT rather than FPU. Anyway, so that's a historical issue. Returning to our Toda problem and the fact that we have all these terms, the question is, how does it behave? And the way we study the behavior also needs to be carved out a little bit. I don't have it on the slide, so I'll tell you orally. Might want to write it down if you want, because it's not in my notes. Basically, historically, these problems were studied by first framing them as harmonic problems. Okay? When you solve the dynamics of a harmonic problem, the historically important way or the historically valuable way is by using the frequency picture and the normal mode analysis. So we basically write it as coupled equations, then we do e to the I omega t, and then we write it as an equation in omega. From that, we can calculate the spectrum, and we can solve it as eigenvalue problem. We can basically get the frequency spectra and so on. Now, when you do these nonlinear problems, how would you begin? You can begin with normal modes, and you can think of the nonlinearity as a perturbation on the linearity. So it's a perturbation on the linearity. Linearity is strong, nonlinearity is a little bit. So then you can start with the normal modes. And just like Fermi-Pascal and Singo did, you can see if the normal modes, they remain fixed or if they start to exchange their energies, which was the pictures I showed you long time ago now in terms of those recurring oscillations, energy oscillations of the Fermi-Pascal problem. So people have historically tried that approach. So therefore, a lot of people approach these problems still using the normal mode entry point. Now, I have mostly never done that because being trained as a non-equilibrium statistical physicist in linear response theory, I like to think of systems that I have my system, I give it a pinch or give it a pluck or something, or I give it a push, and then how this push dissipates throughout the system. That's how I frame dynamical problems typically. Perturb the system, see how the perturbation disperses. This is the way linear response theory is set up. And that's what happens in experiments also. Because suppose I have my phone, I want to understand my phone, I let my phone sit, I bombard it with neutrons from a source, the neutrons come and slightly perturb this phone, and then I can study using whatever methods that are appropriate for this phone, how that perturbation disperses throughout the phone. So this is how experimentalists study these problems. And so I like to do it that way because to me that is physics. So what happens in these systems is very interesting. You take a chain, mass spring chain, and let's say I let one mass, focus on one mass and essentially kick it. I don't kick it so hard that the system gets riled up very much, but I kick it a little bit. Linear response, the kick shouldn't be much. If the thing destroys the Hamiltonian, then it's not linear response. Gentle kick. So what I did was I asked the question that if I take a total chain, infinite chain, let's say, and I do a little kick, what happens? The answer is quite complicated. The answer is that you still can get a soliton if you arrange it right, but you may have to wait a bit. And this is kinetic energy here. This is space along the x-axis. So you can see that if a kick is given like that, you can end up with a propagating solitary wave or a soliton, whatever you call it. Let's see what it is. These are pictures at different times. The pulse is moving, in this case, from right to left. So at the early time, t equal to 0, the pulse has been created and it ends up at 1400, meaning at particle 1400. It's a long system. This is where we start our stopwatch. Then we measure where the pulse is at t equal to 10. It was before 1400 actually. 1400 is right here where I have my arrow. And now it is slightly past 1400. So it's moved a little bit further to the left. And after 30 more units of time or data recording, it's at about 1300. And after 100, it's at about 1100. So if you examine it, you'll find the pulse is moving at a very fixed speed from right side to left side. That depends upon how it's been perturbed. Because it's a long chain, it may be perturbed in the middle. You don't want to go near the boundaries because it's supposed to be an infinite chain. Your boundaries may be at minus 5,000 plus 5,000 in a numerical system. So all that reason why you see this 1400 or near 1400 as the point where measurements have been made. And you can see something very interesting. Toda's theoretical solution is the dashed line here. And our numerical solution in this case is a solid line here. And I can blow it up a little bit, I think. And you see that they are very, very close. They are very, very close. They are not exact, but they're very, very close. And they are not exact because Toda's solution was not generated the same way as ours was. Okay. Toda generated a solution for an actual infinite chain. We generated our solution for a finite chain which boundary is far, far away. So when you generate a soliton, there's always a little bit of tail formation, meaning some small energies come later. Not all energy you have given to the system becomes a soliton. If that were to be the case, you are inevitably over-constraining the system. Nature decides how much will be soliton. Nature has given you the Hamiltonian. You give it energy, but nature decides what it's going to make. You can't say, I'm going to give you the energy and you have to make it into a soliton, but this is your interaction. Nature doesn't care for that kind of dictation from us. To make my point clear, it's the lower picture. No, not the lower picture, next picture. You see, this picture is seen from above. These lines are energies, propagating kinetic energies. And here you can see that at t equal to 0, around here is where the pulse starts. This is the soliton that you saw. This is the crossing that you saw. Whereas this gray cone is nothing but that weak energy tail that's coming after it. One reason why we haven't done a long range is because then you would have seen the tail. That messy tail is showing up here. This is what's coming. But you see, even the tail-tail interaction is very smooth. There is no dirty, chaotic stuff as far as we can tell. The fact that nothing is happening as the solitons are passing through each other is what makes it a soliton. If there was something happening, it would have been a solitary wave, which is more imperfect, more realistic, more natural than the mathematically perfect soliton, where they pass through each other and completely recover themselves. Yeah, Tony.
Solitons don't interact?
They don't interact. They interact only through a phase lag. It's like this is going left, this is going right, or rather the other way around. And they interact in the sense that when they pass through each other, they slow down. There's a phase lag, and that's it. They're unscathed otherwise. That is why I try to differentiate between a soliton and a solitary wave. All the solvable integrable systems thus far have only shown solitons. Nobody has shown a solitary wave as far as I know. You can see we have made some settings here. Let me go back and this is the Toda potential we had taken, which is pretty much exactly the form that you saw in Toda's paper. K1 over K2, there's a K2, there's a K1 over K2, there's a K3, K3, 0. In this case, the values taken for K1 and K2, K3 is 0, is K1 is 1, K2 is 10. So if you go back here, that means the denominator here is large, and e to the minus K2 is e to the minus 10 times this. And this is also a small number. So that's what it means. So this is the study of the Toda problem. And let's go and see how Toda solved this problem. Toda was quite a talented physicist and mathematician, I would say. I mean, it's not often that you come across people like that. It's the only discrete integrable system that we know of so far. The entire human race knows only this one. How did Toda do it? This is Toda's Hamiltonian. So a over b to the minus b, blah, blah, plus a. You set up the Liouville equation, dp dt is dpj dt, pj comma h, commutator bracket. You work out the commutator bracket, quite simple. That's the way we have done it from doing the recurrence relation business. And then you quickly see that your dpj dxi should be 0 because x and p are independent variables with respect to each other. And that, of course, means this first term falls off, second term only matters. And so you compute the del h del xj, and here is the computation of del h del xj. Here. So you see at the end of the day, Toda's problem can be essentially written in terms of a subtraction of two exponential terms, right? E to the minus beta xj plus 1 minus xj minus e to the minus, not beta b, xj minus xj minus 1. And then if you go to the next slide, you begin to see that I've just readjusted the looks of the thing a little bit. I've just flipped this order because a minus sign comes in. This is minus del h del xi, right? That's minus gradient of the Hamiltonian, gradient of the potential. So that minus sign means this is flipped over. And so you have just a reverse order of how these two terms are arranged. That is your equation of motion. That is Toda's equation of motion. And Toda's equation of motion here is written in a very classic kind of style that is preferred. Here you see the equation is written for nth particle, and then the equation is written for the n plus 1th particle, and then the first equation is subtracted from the second equation. So what happens is you have double derivative of xn plus 1 minus xn, and on the right side, this then becomes as follows: xn plus 1 minus xn, xn minus xn minus 1, and xn plus 2 minus xn minus 1. Almost same as our harmonic oscillator structure, excepting exponential terms. And then what one does, and this is the nice part of the trick, is one replaces xn plus 1 minus xn by a bond, in this case, Rn. And so the equation is written in a somewhat more tight form. M d2Rn dt2 equals A 2 e to the minus Brn minus e to the minus Brn minus 1 minus e to the minus Brn plus 1. So this term, that term, and that term, with the appropriate signs adjusted. Now, so this is Toda's equation, and this is what Toda wanted to solve. So I simplified it further by making m over a equal to 1 and b equal to 1. So if you see, let me do this. So this is our b here. and M, and this is A. So you essentially got rid of all these constants. Figured why screw around with constants for nothing? Nothing to benefit right now. And that brought him to this very beautiful simple form, and that is this form. Most mathematicians, when they talk about these equations, start right around here. This is where they start. Okay, so now you see it takes another very interesting step. For me, at least, quite non-intuitive, I must say. He defines e to the minus Rn minus 1. So basically, the polynomial series as one variable, eta n. And then he makes this 1 plus eta n into his term of interest, because this 1 plus eta n then becomes e to the minus Rn. And then this minus Rn, therefore, is just the log of 1 plus eta n. And then he writes the whole equation in terms of this log of 1 plus eta n. How counterintuitive is that? This is what happens when you screw around with an equation for a good long time. You begin to develop insights that you otherwise won't have. And Tora nailed it. No, there's something I should point out here without taking too much time. Japanese people went through this Meiji restoration phase. Did I ever tell you this?
No.
You see, Japan came out of a pretty rigid imperial setup into the 20th century. Of course, there's still an emperor, I think. And Japan excelled in whatever it did. It's an island country, not necessarily very strongly connected with the rest of the world. They were great warriors. Of course, they did a lot of massacres in China and Southeast Asia. We know that. Everybody hated the Japanese. Led up to World War II. And in fact, it was basically dropping the bomb on Japan that's ended the war. But Japan also went through this phase, which is called Meiji Restoration. Look it up. Meiji, Meiji Restoration. And this was a phase in which the Japanese people, their creative energy was unleashed, and their drive to single-handedly solve important problems came to focus. If you look at physicists in Japan, you'll be astonished that countries like Germany, countries like America, countries like Great Britain, France, Italy, Greece, they had such a long heritage of incredibly important people who had contributed to a culture of research and culture of creative analysis of important problems. We know these names. Japan, on the other hand, had very little to go along in the late 1800s, early 1900s. But if you look at the contributions from Japanese physicists, for example, how many Nobel Prizes they have won, coming out of nowhere, doing earth-shattering work, it makes you wonder, how is that possible? How is it possible for a teeny tiny country, isolated, to do this? I don't know the answer to that question, but I know I had a Japanese student And I know that there is no student like him that I've ever had. So this guy, maybe that was his training from school days as a kid. First of all, he, when he took up a problem, he hardly ever asked questions, almost never. And the question would be, hey, Dr. Sen, can you tell me if I should try this method or that method? I've checked out both methods should work, but I can't decide which one to try first. I would sit Yoichi down and we'd have a chat and then say, maybe you can try this one first. It makes more sense to me. I said, okay, I'll try that one first. And so this is the level of advice I gave to Yoichi. He solved the problem. I gave him some expert advice. Uh, and I realized that he didn't need me. He could have done a PhD completely by himself. It is just because he needs a PhD piece of paper, I had the great luck to be his advisor. But that is how he was. And I think many Japanese people are like that. They don't need your help. They can do it themselves. They are that capable and strong. And the reason why they are so is because they work smartly and they work very hard. In fact, I drive my students crazy by pushing them to work hard. I had to do the opposite for Yoichi. Yoichi, calm down. Quiet now. You, you rest today. Tomorrow we'll discuss it. And then tomorrow he would come. Hey, doctor said, I've solved the problem. I said, what do you mean? No, I was up all night doing it. This is how sometimes he would make himself sick. But Japanese culture has something in it that completely blows my mind. I spent very little time in Japan in my life so far. I would love to go back and literally spend a month observing some of these people. I don't know if that'll ever happen. But anyway, so coming back to the equation of motion now written in terms of this log of 1 plus eta, this is what comes out. You have this minus d2 dt2 of log of 1 plus eta. And then you have the same old structure that you had. So observe that this structure here is exactly the same as this structure here. No major difference. And then he reorganized it a little bit. But now he did something interesting. He replaced the representation by defining this variable s. And this s is essentially the first integral, not of log of 1 plus eta, but of eta. I would have thought he would go for the log of 1 plus eta. No. While that was his goal, he actually integrated eta. Right? And eta, of course, is this, e to the minus rn minus 1. He focused on this guy. This was his laser focus quantity. Very non-intuitive. And then he showed that this equation can be written in this first integral form of this equation. Still a second order equation. And rather daunting, I might add, with s double dot and s dot here. If somebody gives me this equation to deal with, I'll honestly tell you that I'll have some trouble. I'll have some trouble trying to come up with a form. Now, look at what Toda did. This is something to behold. Toda decided to play with hyperbolic functions. Yes, Vivek.
Can you go back?
Yes.
I mean, if we just look at this equation, like last equation, Sn
Yeah.
plus 1 plus Sn minus 1 minus 2 Sn, doesn't it look like Gain loss equation.
Well, it looks more like a harmonic oscillator equation, but gain loss equation typically has a gain and a loss term. Here it has three terms. Huh? Anyway, it's a gain loss equation because you have something being pulled and something is being pulled with respect to another. So gain loss equation, I've never thought of it that way, but probably I would interpret the right-hand side more as it looks like a spring. Is your internet okay?
Yeah,
Internet
yeah.
is. I would think it looks more like a equation of masses connected by springs on both sides. But you have to understand what a solitary wave is or what a soliton is. What is a soliton? You see, a soliton is a velocity pulse. That means if you have a mass spring chain, when you have given the perturbation, a few of the masses and the springs in between, they are carrying the energy. Nobody else is. So it's a pulse of energy. If you look at the kinetic energy, the pulse of energy. So this is, let's say, the velocity in the initial part of this. If you take a snapshot of the pulse in space, freeze it in space at a given time, then in the front end and the back end has little energy and the middle has high energy. So that's your pulse. And this pulse is moving along like that in time and space, right? That's a soliton. It is a soliton and it's special because it does not disperse, because most of these guys would disperse. All right, so now what happens is if that is the velocity, so suppose the velocity, if you look at the functional form of the velocity, or the velocity square rather, you will find that there is a sech square form buried in it, hyperbolic second squared form. It's not exactly a Gaussian. It looks like a Gaussian, but it's actually a hyperbolic second square. That's relatively easy to make out by fitting. So if your form of a solitary wave's kinetic energy is hyperbolic second square, then what must the displacement be? Displacement should be tied to a hyperbolic tangent function. Okay, so x must be rather displacement function must be of the order of a hyperbolic tangent function. Then the velocity would be a derivative of hyperbolic tangent. It is sinh over cos. That one becomes a set square if you do it. So what happens? A set square comes in if you do it, when you do it. So I can't get into Toda's head, but Toda expected hyperbolic functions to come as a solution. So if you have hyperbolic functions that must come as a solution, then you have to imagine that these displacements and all these guys are somehow hyperbolic functions, and these are derivatives of hyperbolic functions. So this is what he did. He thought about this well-known identity. Hyperbolic tangent of u plus minus v is tan u plus tan v, 1 plus minus tan u tan v. Even a fifth grader knows it almost. Not a fifth grader, maybe seventh, eighth grader knows it.
11, 12, you mean?
And nowadays, I don't know what they have done. We had trigonometry in class 8. So I taught it to my daughter and when she was in class 5. And I created danger for myself because by the time she was finishing class 5, she could do this kind of trick faster than me, which completely blew my mind because I showed her the tricks and she could employ the tricks much better than I could as a kid. So in my opinion, they should be taught younger, not older, because kids learn better. That was my experience. Of course, if I tell it to the school board, they might kick me out of the area because I don't think any math teacher wants to teach it in fifth grade. Um, but we had trig pretty early. We had trig already coming in by the time we were in eighth grade. Anyway, so then he looked at the fact that if he thinks about the displacement functions or this Sns as tanh, then there should be a function like this that would be of interest, tanh u plus v plus tanh u minus v minus 2 tanh u. And then, of course, he knew that well-known identity that sec squared plus tan squared is 1, just like sine squared plus cos squared is 1. So he then identified the following identity as a close match, this identity as a close match to this form. Close match. When it's a close match and you haven't done it, it should make you very frustrated. I'm sure he went through that. And he realized that if he let the displacement function somehow be like a tanh function with a coefficient before that, then he could put this guy in that form. And if the beta function can be identified with the sin square function, he had nailed it. See, set square tanh u, beta. Set square u. So if beta could be sin square, its problem was solved, essentially. That's exactly what happened. So he assumed that Sn of t is e to the beta t plus alpha n, and then everything started falling in place. And if and only if beta square is sin square of v and v is alpha, you could essentially solve the whole thing in closed form. And therefore, e to the minus Rn minus 1 turns out to be a series function of all these set square functions. Actually, he was inspired by the sphenoidal waveform also. It turns out that how beautifully he managed to solve this equation in closed form. And it is because it can be done in closed form so well. The problem of Toda with boundaries at infinity could be done. But what most write-ups won't tell you, I will tell you. If a problem is integrable, no matter what the boundary conditions that you impose are, that problem is still integrable. It turns out that integrability is a fundamental property of nature somehow. So no matter how ugly boundary conditions you impose on a Toda problem, no matter what perturbations you generate, you can generate even random perturbations. Your problem will still remain integral. And it is because of this property a great deal of fascinating insights have developed, which honestly are too complicated for me to follow most of the time. So recently, in fact, it was last month and earlier this month, we were working on a Toda problem. But this Toda problem had fixed end boundaries. I think that's what it was. So we had fixed boundaries, and we were getting extremely complicated phenomena in it. And I tried very hard to see if I could establish that this solar problem with those boundary conditions become essentially chaotic. And I failed. Meaning that these integrable systems, they may look chaotic, but they'll never become fully chaotic. So that's also a very important piece of knowledge that I'm trying to share with you, that an integrable problem is an integrable problem. That doesn't mean it has less complexity than a non-integrable problem. It may have just as much, but you will still fail to make it chaotic, fail to make it go to equilibrium eventually at the end of the day. It simply would refuse to. Why? I wish I knew, but I don't. You may have noticed I've not gone back to the discussion of the Kolmogorov-Arnold-Moser theorem, which I covered on Tuesday. I decided to take it off from coverage. And I'll tell you in a second why. You see, the dust has not settled in deciding what is non-integrable. It remains an open problem. And there are no definitive, conclusive tests that you can do on an equation, on a dynamical equation, to establish non-integrability. You can't say, I've applied so-and-so test on this and it's non-integrable. We are not there yet. It's a very real problem, right? I mean, suppose your job is to predict the stock market. Stock market is chaotic. You are in a chaotic state. Can you really predict it? Maybe you can predict it to some point, but you can't predict it beyond a point. That would be because of non-integrability at the end of the day. If it were fully integrable, it probably would be more predictable. So there are real life consequences of this. So essentially, it turns out that, the Kolmogorov-Arnold-Moser theorem doesn't resolve this problem. It sheds light on this problem. Kolmogorov-Arnold-Moser theorem says that if in a system, the time evolution of, let's say, two parts of the system, let's say particle 1 and particle n. If particle 1 is not running away from the system, it should pretty much have a closed trajectory in the system because it is somehow doing some kind of periodic thing within the setup. If it's not doing something periodic, if it's doing something wild, then of course it'll be chaotic most likely. It'll go to equilibrium. But let's say it is doing something in such a way that the PQ phase diagram plot is a closed loop. So it is a frequency. And suppose this nth particle is also doing the same thing, but in a different orbit. Orbit meaning in a different PQ phase diagram. Now, if this omega and that omega are related by integer numbers, Kolmogorov-Arnold-Moser theorem says that that can be a problem because there can be resonance between these two orbits. And if there is a slight mismatch, this resonance can get very bad, or this resonance can get dissipated, depending upon how the system goes. So the entire focus of the Kolmogorov-Arnold theorem is about these orbits. Whereas what we are discussing here, I think is a little bit more difficult to understand with these orbits. And orbits don't give us a conclusive answer either way. It doesn't dictate what is non-integrable. It just is more focused on the route to chaos, if you will. If that is to happen, if there's a likelihood of that to happen. So mathematicians have now been completely obsessed for very, very good reasons with the issue of can a non-integrable system then be approximated by an integrable system? And most of my close friends who are very, very good. I mean, these are some of the top guys in the world now who are in this field. They also don't know the answer, but they are always attempting to mimic non-integrable systems with integrable systems. They are quite optimistic. I am not. My gut feeling, for whatever it's worth, is that if it's non-integrable, it's non-integrable, man. You're not going to get it. You can get close. It may look close. It may smell similar, but it won't be the same. You're going after that rasgulla, you're not going to get. You're going to get a close approximation, but not the original thing. Poor Tony doesn't know what a rasgulla is. Right, Tony? Rasgulla is a Bengali sweet that looks like a spongy sphere, white in color, and it's sweet, and it's very nice usually. You should go to an Indian store and try and get some canned rasgulla and have it at home. There is a dark, deep fried version, which is called, what is it called?
Gulab jamun.
Gulab jamun. Gulab is actually rose, right? Gulab
Rose.
jamun, but gulab jamun. Gulab jamun you'll get. You can have that. I like it a lot. But rasgulla is Rasgulla, rasgulla or rasgulla, whatever it is. It's sweet though. If you don't like sweet, don't eat it. So what I'm saying is that it's very difficult to have a good quality, authentic rasgulla. So if you are going after a rasgulla, which is a non-integrable problem, you can get an integrable version, which can be a close approximation to a rasgulla, but you won't get the real rasgulla, is what I'm saying. So I should close here now. So at this point, I was going to come down to a non-integrable problem, and that's our Fermi-Pascal simple problem. This is a non-integrable problem, and this is a mess of a problem. But something happened in 1965. So remember, 1954 is when Fermi died. November of 1954, he died of stomach cancer, actually, as it says here. Not stomach cancer. It doesn't say stomach cancer. That's what happened. So, these people tried to solve this problem. And of course, they wrote that famous report, which was never published, excepting as a Los Alamos report number 1940. But in 1965, 10 years after Fermi was gone and this problem was done, there was this very, very interesting paper by Norman Zabusky and Martin Kruskal in Physical Review Letters. And they said that, look, if you take the alpha FPU problem is, remember, it's this one. This is the alpha. Here, alpha, as I said, is small compared to this term. So it's more linear and weakly nonlinear. If you take this problem this side, and if you go from the lattice to a continuum, so A goes to 0, Na equal to L, N goes to infinity. That is a lattice to a continuum. Then you can write with some approximations the equation of motion for the Fermi-Pascal-Ulam alpha problem into a Korteweg-de Vries problem, into a continuum, that 1895 Korteweg-de Vries problem. And that gives you a set square solution for the velocity. This paper is very accessible in Physical Review Letters. If you Google it, you can get it. I won't get into this paper. It's not super simple. It's also not difficult to understand, but maybe more difficult to understand if you want to get into the detail. Big picture is easy to get. But the point is that they said that this alpha FPU problem can be moved in continuum limit to a Portevec de Vries problem. That actually is not rigorously true. Portevec de Vries problem is an integrable problem. Alpha FPUT problem is not an integrable problem. So therefore, you don't get all the features. You don't get the full Rasgulla. You get an approximate Rasgulla. And that's what they showed. And that's why this is an important paper. In fact, it's a super important paper in the pantheon of these important papers. So I'm going to close here now because I want to discuss the FPUT problem and what non-integrability brings you. That is worth looking at. So at least you understand that non-integrability, not being able to track non-integrability's consequences can be a big problem. How big a problem? Life and death. So we'll come to that. So let me close here. I have already overshot my time. I was planning to get a little bit further along, but we'll get there. Anyway, no hurry. Okay, we're done. I'll see you on next Tuesday.
Good night.
Bye.